Everybody, first of all. So this is going to be part 2 of this discussion about eigenstate thermalization hypothesis from the point of view of violations of ETH. So let me just briefly recap where we stopped. So this is the plan of things that I wanted to touch up this discussion. And yesterday we stopped discussing integrability and the presence of local symmetries for systems without disorder. And I just want to start again by doing the usual remarks. So I invite people to integrate whatever I'm going to say. So I know that there are many people here who are actually working on some of these subjects. So please feel free to add any comments along the way. And related to that, so there was a question yesterday that was addressed by people in the audience. So I just wanted to show. So the question was related to the decay of eigenstate to eigenstate fluctuations of diagonal matrix elements for ETH satisfying systems. And here is just an example. So in fact, indeed, there is a lot of numerics. So I took it from this particular paper here. So they look at this spin chain. They look at matrix elements of this current operator. And the plot that I'm referring to is in this little inset here. So this is fluctuations of matrix elements of this object with respect to different eigenstates at the same value of energy density divided by L as a function of length. This is a log scale. And so you see that for sufficiently large length, you have this exponential behavior which sets in. So this was pointed out by people here, but I just wanted to show a plot. Okay, so let me go back to this, let's say, little summary. And what I'd like to start with today is something that is slightly related to this idea of integrability and integrals of motion, but which also has this extra ingredient that is the presence of disorder. So is this my fault? No. Okay. And this brings me to discussing this issue of many-body localization. So many-body localization somehow was already put in at the beginning when I showed you these results of this experiment in the Immanuel Bloch group about the imbalance and its relaxation to finite values after quantum trenches. So this was a realization of unitary dynamics for an Hamiltonian that contained these local fields, which were very, let's say, inhomogeneous. It was a particle Hamiltonian in that case. So here I'm rephrasing everything in terms of spins. So this is another example of Hamiltonian which can show or is expected to show many-body localization. It's a spin chain. So this is very similar to the ones that I wrote when discussing clean integrability. It's an X at Z chain. But then you have this extra term with all these local fields. So these are coupled to these spin operators along, let's say, the Z direction. In the Bloch sphere, and all these fields are very different from each other, and you can actually take them as being random variables, which you extract from some distribution, let's say uniform distribution that has a width proportional to some h, and h is what measures what is the strength of the disorder in this Hamiltonian. So strong disorder corresponds to wider distributions for this field. Now, this is obviously it's what you're writing down is a family of Hamiltonians here. So for each realization of your randomness, you will have one particular Hamiltonian with its own eigenstates and its own spectrum. And what you would like to do is to say something about typical realization. So what are the properties of this family of systems which hold with probability that, let's say, goes to 1, and the probabilities with respect to the disorder realizations. Now, what can you say? So in this case, so I wanted to stress that there is this dependence of the spectrum, of course, on all the parameters of the Hamiltonian, which are many in here. And I wanted to stress this because this makes it clear that it should therefore be very difficult to be able to, let's say, write down explicitly what is the structure of the eigenstate for this problem, as we can do for integrable systems via the ansatz, for example. But nevertheless, we can still say something about these eigenstates, and somehow in a way which is a bit loose. What I would say is that in general, you find that when this disorder is strong, the full eigenstates of this full Hamiltonian with this order and with these extra terms that do not commute with sigma z, in some sense, very similar to, or quite similar to the eigenstates of the Hamiltonian that you would have in presence of only the disorder. So if you switch off this term, of course, your Hamiltonian is trivial. It's diagonalized in the basis of product states of the sigma z. So all the eigenstates are simultaneous eigenstates of these operators as well, and you know how to solve the problem. Now, the statement is that if you switch on this extra term and you keep this h sufficiently large, so sufficiently larger than the other couplings that you have in here, the full eigenstates will be somehow weak deformation of these product states in the basis of operators, which couples with disorder that in this case is sigma z. And what does weak deformation mean? Well, if you want a picture, what you can think of is that you have your Hilbert space, you have these product states in your Hilbert space, product states of sigma z, and what you find is that the many-body wave function of this object here are in some sense localized distinctly of each one of these product states in a notion that is similar to usual Anderson localization space, except that you are rephrasing this in the Hilbert space of your many-body problem. So you should be a bit more careful about this, but I think that the good picture, the good way to think about this problem is roughly this. Now, what does it mean? Well, of course, you immediately realize that this implies violation of ETH. So assume that now you take two of this many-body wave function, again, with the same energy density. And let me take an energy density which thermally would correspond to an expectation value of this sigma z operator that is 0. So for example, if I look at the many-body spectrum of my system, I go in the middle. The middle corresponds roughly to infinite temperature, if you think about the thermal formulation of the problem. And I should expect, if ETH holds, that the expectation value of this sigma z is equal to 0 in all these different eigenstates. But now, of course, if I'm telling you that these psi alpha are somehow very similar to product states in the sigma z basis, then what you easily expect is that you take two different eigenstates, you go and measure this sigma z, and you find a result that is not too different with respect to the result that you would find in a product state on this basis, namely either plus or minus 1, depending on the sign of the particular spin at the particular site I that you're looking at. And this is different from 0, so clearly you have a violation of ETH. You are able to discriminate and distinguish eigenstate by probing, in this case, very local operators like a single spin. And you can also say something about properties of entanglement of these eigenstates. So this was discussed, of course, in other lectures. So here I'm thinking about, let's say, half system entanglement, entropy. And what you find is that in general, let's say robustly, all these excited states have a very low entanglement. So exactly in the same vein as product states that you would have if you had only the disorder term in the Hamiltonian. Okay, so this is the now here I'm showing a picture of numerics that is actually quite old. This goes back to 2010, but just to give you an idea. So what they are doing here is measuring. So I don't think you see this, but this is the difference between what they call mi alpha n and mi alpha n plus 1. So the idea is the following. So n here labels an eigenstate in the spectrum. So what you do is you diagonalize this Hamiltonian. You pick up two eigenstates which are subsequent in the spectrum. Then you look at the expectation value of this sigma z operator at a given site. So let me say that this site is I. And you do it for a fixed realization of disorder that here is labeled by alpha. So you do it for the eigenstate psi n, and then you take the difference of what you get with the same object for the following eigenstate along the spectrum. And then you take the log of the difference and you average over the sites and over the disorder realization. And this is what is plotted in here for different system sizes as a function of this disorder, which increases moving up along these curves. And the idea is that if you have ETH, of course, this expectation value will converge to the same object, which is the thermal one. So the difference goes to 0 with system size. And so the log goes down to minus infinity, which is kind of what you see clearly when the disorder is weak. But then you see that if you increase disorder, at least for these system sizes, it looks as if this difference is non-zero, but it remains finite, and therefore the logarithm remains finite, and the dependence on system sizes is in fact very weak. And you can look at numerics for, let's say, larger system sizes in subsequent papers. Of course, there is a bound on how much you can do with exact diagonalization. I think that now people diagonalize systems like this, reaching sizes of maybe 24 or something like this, but no more than this. Okay, can one say something more precise at the level of theory? So, of course, there's a lot of, let's say, physics-like analytical work on these systems. Well, maybe not a lot, but there is some. But here I wanted to mention what is perhaps the only math work that you find in this community. If you think about many-body eigenstates in the middle of the spectrum, so not at the edges. So you are away from the many-body ground state here. You are at excited energies. And this is work by John Imbrie, who essentially in this paper looks at one particular random Hamiltonian that is seen here, is more Ising-like. And the statement that he proves is essentially an ETH statement. So you see, what you say is that if you choose, so here you have a sigma x, sigma z, and sigma z. All the couplings in his case are random, but the idea is that if you choose this gamma coupling associated coupled to sigma x, which are small enough, so meaning for gamma small enough, you can find a case such that you can put bounds on these expectation values of the sigma z operator in the diagonal matrix element in the basis of eigenstates of the many-body Hamiltonian, and the bound tells you that in fact this expectation value is very close to 1. That is this idea in here. Okay, so I, let's say, introduce this by making a connection to integrable systems. So one may wonder where is integrability here. And the idea is that you can kind of understand what is going on in these systems by making this observation, which was made in this original works around 2014. And the observation is that also in this disordered case, you are able to, or you expect that there should be conserved quantities, exactly as in clean integrability. At fixed realization of disorder, for one given Hamiltonian, you can find some set of operators which commute with Hamiltonian, which commute with themselves, which are local. But the crucial difference with respect to what we discussed yesterday is precisely in this notion of locality, that here is very much influenced by the presence of disorder. So by this idea of localization and exponential tails that are usually a signature of localization problems in disorder. And how does this translate in here? Well, it translates in the fact that if you ask, so suppose that you are looking at a problem in the lattice, and you ask, what is, if you want, the norm, so the strength of this operator at different sites in the lattice, so how does the norm behave in space? What you find is that these operators have a norm which has a profile that is exponentially localized itself. So the norm of the operator will be large only in the vicinity of some site that you call maybe the localization center of the operator, with some typical length scale that you can call the localization length. And the action of this operator on degrees of freedom, which are at sites which are far away from this region, is actually exponentially bounded, or you expect it to be exponentially bounded. And this is a notion of locality that is somehow in between being strictly local and local in the sense of, say, the Hamiltonian of your system. It's in between because you're not strictly local, your operator essentially acts on all sides, but you see that you can kind of truncate it in some compact region, and you will find a very good approximation of your symmetry, which commutes with your Hamiltonian up to exponentially small corrections. No, you do break integrability in the clean sense. You have another type of integrability which emerges precisely because you're putting disorder in there. But the mechanism behind it is a bit different. It's an integrability that is more due to localization around the disorder basis rather than the fact that you have couplings which satisfy relationships that give you algebraic structures that give you the Gaussian function, which is what happens without disorder. So your disorder term is, or if you want, you don't need to tune this delta, you don't need here, you can put, let's say, also next to nearest neighbor spin shift terms. That's fine. What is important is that you have this term here, which is strong enough. Yeah, maybe it's confusing that I put XXZ here, but you can generalize this. No, so they are truly conserved. So if you go back to, okay, the existence of this object is something that you can somehow deduce from what is proven in here. And the idea of the proof in here, so let me try to summarize it. I don't know how clear it is, but what you want to show is that you start from this Hamiltonian here, and you want to fill in the unitary operator which diagonalizes this Hamiltonian. And the key here is to show that this unitary operator has some property of locality, so it admixes only, let's say, degrees of freedom that lie locally in space. And if you show this, then you have this unitary which diagonalizes the Hamiltonian, and you can apply this unitary transformation to your, let's say, sigma z degrees of freedom. And out of this, you get a new set of operators, which are conserved, so which are these guys in here, which have the same algebra, of course, of the original sigma z, because of the original sigma, because you apply the unitary, and which are local because the operation, the rotation that you're applying is have this property of preserving locality. Yes, absolutely. So in here, I think that one shouldn't think about, so I think that the way one should think about this is the following. So you can always kind of build operators which satisfy this relation, either for weak disorder, but the locality is lost when you go to weak values of disorder. So you need disorder strong enough so that what you are constructing is actually have this local property. Yes, so each sigma z, it's like, it's a bit a lambda adiabatic. I mean, it's like when you construct quasi-particles from non-interacting degrees of freedom. So you have some sort of analytic continuum. Okay, it's not exactly like this, but one can think that for each sigma z in the basis, I have one of these objects that is, let's say, localized in operator space in the vicinity of this sigma z. So you have as many as the sites. If you're thinking in dimensional universes, yes, it's L, so log of E to B. Yes. Okay. Of course, I don't want to speak for the work of others, but I can maybe summarize a bit what is going on in the community. So this is, well, first of all, this is a proof that you may notice is not published on math journals. And the reason is that, as he calls it himself, is a conditional proof. So there is an assumption in there that he is not able to prove, from which this result follows. And now the assumption, just to state it loosely, corresponds to the fact that what you're asking is that if you take a finite subsystem of your, say, Hamiltonian, the smallest energy gap that you find in this subsystem is not going down faster than an exponential in the size of the subsystem, which is, okay, something that everybody says is very reasonable to assume. And of course, one would like to prove it and not assume it, but this is But this is the situation. Now, starting from, let's say, some years later, 2016, there has been a rejuvenation in the literature of numerics about MBL, and this in part went through looking at observables related to quantum chaos, like this spectral form factor, and then the development starting from there. And then people, let's say, pointed out that maybe the estimates that were based on this early numeric were not so accurate, and that you need a stronger disorder strength to actually have localization. And some people concluded from these numerics, or they interpret such numeric as a strong indication of the fact that actually you have a disorder strength, a critical strength of disorder that has some scaling with system size, and so the transition is not there. And then there is a huge debate: how is this compatible with this? Of course, this is not compatible, and so on and so forth. And then the next ingredient, where I think people here maybe can comment more, is that then people started to develop theories of what should be the mechanism that gives transition to delocalization. And this, I think, should be Marcus, who can comment on this, is related to a scenario of avalanches that destabilize localization in the system. And based on this scenario for the transition, there is some further numerics that tries to test precisely this scenario. So it's a bit complicated to summarize what they do in this moment. But based on these numerics, they see that, in fact, if you assume that the delocalization transition occurs via this mechanism, the disorder strength that you estimate to be necessary to localize is again much larger than whatever level statistics tell you with these measures. And so now this is, I think, the situation. I don't know if Marcus want to add something. But there are people checking carefully, I think. I think Wojciech is working with this. No. Yes, it doesn't even tell you how small it should be. It's a very. No, sorry. Yes, this is confusing. So you have disorder everywhere, but you want somehow strong disorder in the SZ, so weak disorder in the non-commuting part. Okay. Okay, so I just wanted to point out that there are, so this local structure in space actually has consequences. For example, I mentioned that for clean integrable systems, there is this notion of generalized DPH into shells which correspond to fixed density of conserved quantities. Now here you have operators which are really pseudo spins, so you get them rotating the original spins. They have spectrum plus and minus one, so it looks very difficult to me to conceive that those statements can be generalized to this kind of problem. Also, the dynamics of your problem is very different. So this local structure, you can argue that it implies that suppression of transport, which is, of course, what you mean when you speak about localization. The entanglement in your dynamics grows very slowly, and so on and so forth. And these are all dynamical signatures, which are quite different with respect to get in clean integrability. And in fact, the mechanism which is behind this is not this, let's say, algebraic relations, but is rather the fact that you can build up some perturbation theory around the strong disorder limit. And this perturbation theory, you can argue, at least within some approximation, you can easily argue that it is you can argue that it is convergent statistically, so that with probability 1, you find that these perturbative expansions are controlled. And the way, or the reason why they are controlled is what people call in this literature, this idea of suppression of resonances. So when you do perturbation theory, the type of terms which emerge will be terms of the form, let's say, ratios of the coupling, the couplings that you're treating perturbatively, that are these, divided by energy differences between the unperturbed states around which to build perturbation theory. And what may spoil this, the fact that these energy differences that are small start proliferating, and then you get something that is non-convergent. And the idea is that when the disorder is strong, and kind of argue that this is not occurring, so the probability to get small energy differences is such that still it does not kill your perturbative expansion. And so you reach statements like this, which is, if you want, the perturbative kind of statements. So the eigenstates are with the formation of what you get in the strong disorder limit. Okay. Now this was about concluding this column, if there are no more questions. And now I wanted to go to these ideas of weak ETH violation, where I remind that weak and strong here refers to the number of eigenstates that violate ETH. So in this case, this number scales the size of the Hilbert space. In this case, it is smaller, so the fraction of ETH violating states goes to 0 in the thermodynamic limit. But nevertheless, they may still play a role even if you converge to measure zero set. And to give an idea of this, I wanted to recall this argument that is given in this paper, which is the paper where this distinction, at least at the level of terminology between weak and strong, was, I think, introduced. So this is an example that is very simple. So they look actually here at a system which is integrable, is a chain of oscillators. But at least it gives you an idea of why atypical things may matter when you think about dynamics of the system. So let me summarize what they do. They have this coupled oscillators, which is, of course, an internal that is diagonalizable. So you can introduce number operators associated to excitations with this frequency of omega. So I'm not writing down the solution, but you may have a look at the paper here. And then they think about dynamics in terms of, again, quantum quantities. So they choose an initial condition, which I think is the ground state at a fixed value of the mass, which I call initial mass. And then they say, okay, I start from such a ground state, but at time t equal to 0, I change the value of the mass, which of course changes all the frequencies that I have in here. So I have a spec for the new Hamiltonian, and I run the dynamic with the new Hamiltonian, and I look at expectation value of some observable. For example, the one that they take is this linear combination of this one of these number operators. So let's say that the initial state with respect to the new Hamiltonian has a given energy density that I call epsilon 0. And now the type of calculation that you can do is as follows. So you ask, well, you have this observable, you have the energy. You ask, what is the number of many body wave function of these harmonic oscillators, which has a given value of energy density and a given value of density of this observable. And what you find is that this is something which takes a large deviation form. So this number scales exponentially with a generalized or constrained entropy, which depends now both on the energy density and on the constraint on the operator that you are imposing. So if you're interested in this energy density that will be conserved during the dynamics, you plug it in here and you see that you have a whole distribution of possible values of this observable. So there will be a typical value that maximizes this entropy that corresponds to the microcanonical expectation value that I call A thermal of this observable. But of course, there will also be a lot of eigenstates at the same energy density that have a typical values of this observable. So for which A is not the one of the maximum. And now the point is that when you do dynamics, you can reweight these large deviations using the initial condition. So you can do a similar calculation where now you introduce the information on the initial state that you have, and you count the same number, so the number of eigenfunctions which satisfy your constraint, but now reweighted by their projection on the initial state of your dynamics. And for this harmonic oscillator case, you can actually easily compute these overlaps. If the overlap of the ground state with one mass and the spectra with the other mass, you have everything. And you show that this term is exponentially small, so it can in fact bias the others, and you get a large deviation function, which is different because there is an extra exponential term in here. And now the scenario of thermalization is that you fix your energy density epsilon 0, and you want that these two functions are maximized at the same value of A, that is the thermal one, because this will tell you that then the dynamics, again, will converge to a value of A, which is typical from the point of view of your thermal entropy calculation, which is in fact what happens in cases in which this overlap of your initial condition with the spectrum is more or less uniform for all the eigenstates at the energy density that corresponds to epsilon 0. But you can cook up examples, and these oscillators are an example where this is not the case, where actually this initial state weights more states which correspond to values of your observable, which are atypical with respect to your large deviation calculation, static, let's say, large deviation calculation. And this is a scenario for the fact that you do not converge to the thermal expectation value. So the long time limit that you get for this observable does not coincide with the thermal one. And the mechanism here is what I call reweighting of the tails of your distribution, but it's sometimes, in some sense, if you want, it's a simple example, but at least you make the point that even though you have eigenstates which are rare in your spectrum, they can show up in the dynamics if you probe them with the appropriate initial condition. That is more or less what is happening also in the case of scars. Here all, okay, so the crucial point is in this reweighting. And of course, here this statement is strongly dependent on the fact that you have a special example. You can compute these overlaps, and the overlaps are exponentially small, and you can show this. So if you go to the paper, they argue that there are indications from numerics for GGE-like systems that this is the case in generic integrable systems. How much this generalizes to systems which are non-integrable, I don't know. I would just take this as an example of the fact that, in fact, the initial condition is important and can bias a lot. What you would guess is the dynamics just by looking at the spectrum. And as I was saying, this is a bit the idea of scars, except that scar is if you want, even more extreme, because it affects not only convergence to the thermal state, but even relaxation that is this one, yes, because it's basically quadratic Hamiltonian of couple oscillators, so you are integrating it when you do this step. So you know how to compute this number of operators. They are linear combination of momenta. No, absolutely. So no. Okay, I don't be confusing. So you're not surprised by the fact that you don't converge to the thermal expectation value. What I wanted to stress is that the mechanism that you let's say unveil with this type of discussion is making it clear that there is an important role of atypical eigenstates in this, let's say, not reaching the thermal expectation value. Now, for integrable systems, we saw yesterday that all the eigenstates are non-ETH, so you are definitely not surprised by this fact. But you can ask, are there other situations in which I have rare eigenstates in the spectrum, and I'm able, with by choosing the initial condition well enough, to have a dynamics which is non-thermalizing or not relaxing, because I'm essentially probing those rare eigenstates and not the thermal-like typical eigenstates. And this is a scenario for weak ETH breaking. So you don't need that all the eigenstates break ETH, which is in fact what happens also in this system, but you just need few of them and a good initial condition. So I'm sorry, this may be confusing because the example we make is integrable, but I think the point is more general. Hope this answers. Okay. Okay, so now this, of course, brings very naturally to quantum scars. So I know, and I get the feeling that everybody in the audience is working on quantum scars, which is, by the way, not my case. So I will just say something and then I leave it to the others to comment. So this is just a short summary. So I think what you now call in the literature as quantum scars are, again, special eigenstates in your spectrum, which are distributed in energy. So they are, in principle, all over the spectrum. So they are highly excited. They are, let's say, few with respect to the scaling of the size of your Hilbert space. So this is why we call this WKPH. And they are special in the sense that they have properties of, in general, low entanglement, like the eigenstates in the ambient case, and they violate ETH. So there is another property in at least some of the examples of scars in the literature, which is that, which is more connected to this dynamical picture of revivals. And the property is that they are often organized into towers. So what you find is that these special states are equally spaced in your spectrum. So they are separated by, let's say, a fixed frequency, let me call it theta. And what this implies is that if you're able to build an initial condition, which is, let's say, ideally only a superposition of states which are in this subspace of scars, then obviously you should expect revivals in your dynamics, and you should expect revivals with timescales which are of the order of 1 over this frequency that you have in here. And so you expect that you have no relaxation, and this goes back to this Rydberg atom experiment in here. And I think you can even make the opposite statement precise. So if you have revivals in your quantum dynamics, you have prescriptions to construct scarred state of your Hamiltonian. Yes. Yeah, I'd like to come to that at the end. And if okay. Now, what's the mechanism here? So now I'm not telling what is the mechanism for having scarred states. Maybe there is some relation with underlying periodic orbits, so this I'd like to comment later. Now, let me just say what is the mechanism to have no relaxation. Well, it's again this idea that you have these special eigenstates, but in some system you are able to build, let's say, reasonable eigenstates, like these product states for this experiment, that happen to have overlap with these special eigenstates, so which are not crazy states. You can build them experimentally. You can think of them as good initial state, and they happen to have this large overlap with states in this subspace. And this is what is plotted in here. So this is log of the overlap between this initial condition for this particular system here with all the states in the spectrum, and you see that you have outliers which have a much larger overlap, and these happen to be related to the scars. Okay, so maybe more about the mechanism behind. I think there are various cases here. So if you think about this Rydberg Hamiltonian that I mentioned at the beginning, what people understood is that what this is realizing because of this Rydberg blockade is effectively a kinetically constrained model. So you can write down effective models for these Hamiltonians, which are the so-called PXP in this particular case, where what you say is that the dynamics is such that you can flip, so you can excite or de-excite an atom which is sitting at the site I, only provided that the two neighboring sites are such that the atom in there is unexcited, because you want to forbid that you have two nearby atoms which are both in the excited states, and this comes from the physics of this Rydberg chain. So this is a kinetically constrained model effectively, and for this model you can build some approximate, let's say, scars, and you can kind of motivate and justify why this implies the phenomenology that you have in the experiment. And I think this generalizes pretty easily to other kinetically constrained models. So there's a lot of literature, classical literature in the field of glasses, where people came up with different kinetically constrained models to justify slow dynamics of glassy systems. These are models that in general you can quantize. So you have a master equation, you look at the master operator, you symmetrize it and you quantize it. And I think that for the quantum version, in general, you can build scars similarly to what you're doing here. So this is an example for the so-called quantumist model that we may look at. But there are also Hamiltonians which shows scars that are not, let's say, strictly connected to kinetic constraints. For example, unit Hubbard, I would say, is one of the case. And here, I think the idea is that if you you can think of this scarred state as being built by, let's say, generating 1, 2, 3, 4 excitations on top of a well-chosen initial state. And this has to do with these ideas of spectrum generating algebras to build scars. And I refer to this reference if you want to know something more about that, or maybe to people here. No. Adjust the Hamiltonian to that scar. Okay. Okay, so I wanted to just say something more related to kinetic constraint that I think now in the literature is more referred to as fragmentation. So I guess that fragmentation is a term that we could use to refer to the fact that you have your Hilbert space for your system, and you can kind of decompose it into sectors which are dynamically disconnected. And this is a dynamical notion. So of course, when you have an Hilbert space and maybe you have symmetries, you can always decompose into sectors related to symmetries. But here you're thinking about something else. So what you think of is you select some states which are good initial states for your dynamics, so which are in general product states. And then you build the subspaces which are spanned by time evolution starting from this type of product states. And in some cases, what you find is that your Hilbert space decomposes into, in general, an exponentially large number of subspaces which are disconnected from each other, such that if you start dynamics from, let's say, the state psi j, you will never overlap with states which are spanned by the subspace associated to another initial state. And I can build examples of this. So I took this from this paper here, which is called the pair hopping model. So this is just a model which an Hamiltonian which allows only for transitions of this type. So you have, if you have occupied sites with period 3, then you can somehow flip in such a way that the excitation go inside. And here you see that you easily can build a lot of states of your system which are somehow dynamically frozen, and the number of the states is exponentially growing. And you can also simultaneously build subspaces which are not made by few states, but which are exponentially large. So just to give an idea here, this is a state which would map into itself basically by this dynamics. So what you do is you have long strings that correspond to configurations where you cannot do anything with this type of transition, so which are blocked dynamically, and then you have some active region, and you can switch back and forth this active region, and this is a closed subspace for your dynamics. And again, I think that this is something that when you have classical kinetically constrained systems, you can kind of easily generalize. So in classically kinetically constrained systems also have a lot of these configurations which have backbones, which are frozen, which separate active regions. And I think this will carry on smoothly if you quantize this type of systems. And the mechanism is that you have dynamical obstructions, or if you want dynamical barriers. So you have that the regions that can move and have an integral dynamics are disconnected from each other by frozen regions. Okay, so this now would bring me very fast to this last piece. Question? Yes. Yes, which is this case, right? Precisely. So are you asking if I can interpret each of these subspace in terms of a symmetry sector, or whether? So for this statement at this level, I don't think this is the case, so that each subspace would correspond to that you have, let's say, of course, it depends on what you ask about this kinds of quantities. So maybe if you take them arbitrarily complicated and local and whatever, maybe you can associate subspace to those. But I don't know, I wouldn't, well, okay, I don't know how you should think about this. So you say that one should be able to reinterpret always fragmentation in terms of, let's say, sectors in symmetry are associated with some operators. Okay. I mean, to me, rather than conservation, so I understand that here you think in terms of conservation because you have, say, center of mass, or how we call it, that is conserved by these transitions. But it's more natural to me to think about the fact that you have a dynamics which is, it really has a lot of possible transitions that are forbidden because of kinetic constraints. So this is in some sense the same thing as what you're saying. And kinetic constraint obviously generate regions where you cannot do anything because they are blocked, and then this feature is natural. But I think, yes, perhaps if you rephrase kinetic constraint as being generated by some symmetry that you have to preserve, then it's what you're saying. Okay. Yes. So in this simple case, I think you range from few states to exponentially many. For PXP, again, okay, in that case, you do not have exact decomposition as we were saying, to disconnected subspaces, so it's a bit different. But at least for the examples I know, you span over sizes which go from order 1 to exponential. But now I want to keep this idea of thermalizing within subspace and connect to your work, actually, that is on quantum glasses. So that's the last example here. So what type of problem we are thinking of? So let me introduce now another model that is inspired by classical problems of glasses. That is called the quantum P-spin. So what you have in here are, so these are again Pauli matrices. You're not necessarily, you're not, let's say, on a one-dimensional chain here. You are maybe on a graph. You have all these operators on the sides, and you have interactions which are now, you see, higher orders and all-to-all. So you can choose arbitrary subsets of P of this sigma Z operator, and you make them interact with a random coupling. That you have to scale because you want these two terms to be comparable and the energy to be extensive. So since the sum here goes over all possible combinations of the indices, and let's say that you have n of these spins, you have to rescale appropriately the coupling to have the good normalization. Now this part defines, if you look at it from the point of view of a classical Hamiltonian, defines a model that is very standard in the literature of glasses. And it's a model that has an interesting thermodynamics. So if you do classical thermodynamics here, you find that at low temperature, you have a so-called glassy phase, which you describe in terms of the order parameters introduced by Parisian here. So with the presence of replica symmetry breaking. And dynamics is also interesting because what you can say is that the free energy of this system is characterized by the fact that there are many metastable states. So you will have states that correspond to equilibrium free energy, but then you have a lot of states at higher values of free energy. And those are states that you see in the classical dynamics of your system. So you try to equilibrate to the states corresponding to equilibrium free energy, but then you see that your dynamics get trapped into these higher free energy states, which are metastable, and it goes out of equilibrium. So this is the classical model. And then to quantize it, what you can do is to add this flipping term with some transverse, let's say, sigma x operator. And you can now do several things. So thermodynamics of the quantum model has been looked at as well. So I'm sorry that I didn't put the references on that. But you can also interpret this from our point of view, which is that of an isolated system with unitary dynamics. And again, ask about structure of eigenstates and violations or existence or presence of ETH. And I think that this has been discussed in this work. The authors are here, or at least one of them. And I find it's an interesting example of, so far I only discussed diagonal ETH. So this is a case where you have, for example, where you expect violation of off-diagonal ETH. And the reason is that for some reason that relies on the distribution of classical energy levels of this Hamiltonian, what you find is that if you look at quantum eigenstates, you can argue that they kind of clusterize with each other. So you look at a fixed energy density below a given value, and you find that all the eigenstates of this energy density are organized into some clusters. Each cluster has its own entropy. And essentially the states that are within a cluster are well thermalizing. So they are satisfying ETH. So if I take some local operator and I look at off-diagonal matrix element between two eigenstates that belong to the same cluster, I have the usual ETH scaling for off-diagonal matrix element, except that instead of the full entropy, I have the entropy of the cluster in here. Whereas the matrix element between eigenstates in different clusters are much, much smaller. So it's like having this structure in which you have a very weak coupling between these clusters. And the idea is that the, let's say, energy levels of the classical part of the Hamiltonian are organized in such a way that you can argue that when you switch on the quantum part that wants to somehow admix this classical energy level, because if you want the distribution in configuration space of classical levels of energy is non-monotonic, this gamma will only basically admix some of them and not all of them fully. So I don't know if the authors, of course, can give more details on this type of problem, but I think it's interesting because it is an example of violation of diagonal ETH, which also connects, and it's partly due to underlying energy landscapes, which are classical, but which have a structure that is non-trivial. Okay, so I think this concludes this, let's say, set of examples. And the idea was to show that when you have a system which violates this scenario of thermalization, there is maybe some richness in the sense that the mechanisms which are behind can be quite different. So some are related to large deviations and the weighting of the tail in the distribution of local observables. Some are related to kinetic constraint, to symmetries that are sufficiently local to be probed by expectations of local observable, to disorder which generates localization, so which somehow pins in operators or eigenstates in the vicinity of some specific configuration, to non-trivial interplay between quantumness and underlying classical systems which are complicated. And now in 1 minute, I will just tell you what was the idea for part 2. But this is a bit a recap of things which emerged. So of course, all the discussion here was about ETH, so it was phrased in terms of properties of eigenstates of your Hamiltonian. But of course, when you think about quantum chaos, it's very natural to also think at properties of the spectrum. And in fact, people have been looking at diagnostics of quantum chaos and how they break down if you look at problems such as localization. And as I was mentioning, this also is part of the debate on numerics of this system. And in this last 2 parts, I just wanted to mention things that are actually things that people in the audience here are thinking about. So I will maybe just mention them, and then you can have a self-organized discussion. So the idea of spectral statistics was already appeared in several lectures, so I will go very fast. So as Laura explained very clearly when discussing ETH, you can see it as some sort of extension of random matrix theory scaling, where you're adding this crucial ingredient that you're looking at a physical Hamiltonian. So you have non-trivial dependencies on the energy densities that you have to encode in these objects in here. And but there is a limit where you expect to recover for this ETH satisfying system the predictions of random matrix theory that I think Laura discussed in the second lecture. And this is when you look at states which are separated by energies which are bounded by this Paulus energy that for a diffusive system usually scales like this. Now for spectral statistics, you can think about similar generalization of random matrix. You again have to introduce this ingredient of the energy density, or if you want to go from here to here, you have to get rid of dependence on the energy density, and this is what people call the unfolding. So you take eigenstates of your Hamiltonian, you rescale them basically by the energy density, and then you look at the statistics of those. And there are several things discussed in the literature, which goes from local spectral correlations, mainly statistics of energy gaps. So what's the difference in energy of adjacent eigenstates? For this, you have very nice random matrix theory prediction, which correspond to Wigner-Theisen distribution. That is what you see here. This is the LPTS logo. And for systems which violate, let's say, random matrix like statistics, you typically have Poisson distribution, which have absence of line of repulsion, and this is this part of the curve here. And if you are at critical points, for example, for disorder systems, you have intermediate statistics that have been discussed a lot for the Anderson transition and also for the many-body version of that. So this is one possible reference. Now in numerics, usually you do not look directly at distribution of the gap. You look at this quantity, which is ratio of gaps, just because this helps a lot, because you don't need to rescale because you're taking ratios of energy differences. So you, in general, don't need to do unfolding. And this is a quantity called the gap ratio that has an average that you can compute in the Wigner-Theisen case and in the Poisson case. And what you do in numerics is to compare what you get from exact diagonalization with prediction for the average. But this is local correlations. Now, global spectral correlations have been discussed in the lectures before. And one example is this spectral form factor. And the idea is that So you introduce this, let's say, time variable. So I'm not going to let's say, repeat everything that was said. Let me perhaps just show one example of a plot. So this is an example for a disordered Hamiltonian with random fields and XZ plus next to nearest neighbor interactions. And it shows you what you get. So these are strength of the disorder, the different colors. So it shows you what you typically get when you diagonalize this type of Hamiltonian. So this is the average gap ratio as a function of disorder. Different curves are different system sizes. This 0.53 is the prediction of Wigner Dyson, so Poisson, random matrix. This is the prediction of Poisson distribution of gaps. And you see that you have a behavior as a function of disorder. And what you maybe expect in the thermodynamic limit is that this becomes this continues at a point which corresponds to a transition between localization and delocalization, and then you estimate it from the crossings of these curves. And below, I'm showing this spectrum form factor. So there is a lot of numerics on this as well. I just took this figure because I liked it. I think they are showing it. So the tau here is not rescaled, I think, by the well, clearly by the Heisenberg time. But okay, so the idea is you have different regimes. So you have a regime which is kind of non-universal, and then you have what is the prediction of random matrix theory, which corresponds to more or less this straight line, and then you have this plateau when you go to time space above this Heisenberg time. And you see for weak disorder, you clearly see the onset. So this is what we would call the tauless time, where you have this onset of this random matrix like behavior. And then if you make the disorder stronger, this is, well, in this plot, it's very squeezed, but you kind of converge to the curve that you would expect instead if you had a Poisson process. So for Poisson, you can compute the spectrum form factor, and what you get is the curve like this. And if you want to know about debates on how to use these observables to, let's say, prove or disprove the existence of RDL, you may have a look at these references in here. Okay, so now in 1 minute, I will just introduce the other thing that I wanted to tell you. So the first idea was about, let's say, the realization of billiards in very high dimension. And the idea goes through looking at classical problems like what people call constraint satisfaction problems. So there is a lot of literature on a high dimensional classical constraint satisfaction problem. And here I'm giving an example which is taken from this recent work, which works like this. So what you do is we introduce some energy that you can also interpret as a cost function, which you want to minimize. And in this case, for example, the energy is given by a sum of positive terms. Now you have the variables of your system are very high dimensional vectors that, for example, live on a sphere in here. And you build these functions out of components of this vector where you choose coefficients here, J, that are random variable with Gaussian statistics. And then you have many of those. This is a function of configuration. You have many of those which are labeled by this mu, and the number of these mu scales with the number of components of your vector with this coefficient alpha that gives the ratio. And what you ask is that you want to find configurations such that this quantity matches some fixed value P0 that is a parameter of your model. And this has to be true. So you want it to be true for all the mu's. So you introduce an energy which gives a cost when this constraint is violated, that is in this case quadratic. And of course, this energy, if you have solutions to your constraint satisfaction problem, it means that you have some configurations where this difference is 0, and so the energy is 0. And this is what you call the SAT phase. So this type of problems usually exhibit transitions. In this example, these are transition as a function of P0 between regions where essentially you have no configuration that satisfies all the constraint, and this is what we call unsat, and regions where you can find configurations which satisfy the constraints. So you can find regions in configuration space which correspond to 0 energies, and this is what you call SAT. And the SAT phase sometimes has an interesting structure that you can characterize if you ask what is the structure of correlations between configurations in this zero energy manifold. And you find sometimes correlations are simple, but sometimes correlations are complicated and show glassiness. So you have to introduce replica symmetry breaking to describe properly these correlations. And when you are in such a situation, your optimization problem, so if you want, you have solutions at zero energy and you ask, can I reach them by finding the ground state of this classical Hamiltonian? And in this region, you find that this becomes hard, both with simulating annealing, and you can also introduce quantum version of this optimization algorithm, and this is reviewed, for example, in this paper. Now, let's say, loose connection to billiard would be that you now have manifolds of zero energy, and this manifold can have, you are in very high dimension, so you may be interested in characterizing their geometry, which is a question that, by the way, recently is becoming interesting also in other fields like learning, where you introduce this high dimensional cost function that you also want to minimize. And this may be a framework in which you can introduce notions like chaos in a very high dimension. So you can basically ask what would be the features of a Schrödinger problem defined in manifolds of this form, which correspond to the zero energy region of classical constraint satisfaction problem. So this is an open question. There are people here that are thinking about this, so you can ask them. Let me just mention that for the simple problem that I mentioned, thermodynamics, you can solve the thermodynamical problem with quantumness, but this would correspond to somehow looking more at the spectrum of Schrödinger operators in this manifold. Okay, so this is one idea. And the second idea, I will not. Yes, sorry. Okay, now the last question that was raised several times is, we speak about scars, we know about scars in one particle problems, we know that these are connected to underlying periodic orbit. Can we say something similar in these quantum systems? And I think we can, and there are several routes, and people here are working on this, but there is no time, so I leave this to you for the discussion, and I will just stop here. Thanks. I think it's yes, it sounds similar. I think the scars that you have in the Rydberg case are a bit a stronger version of this, but you kind of got the point of why I wanted to go through this example, because in some sense it's similar. And then when I say it's similar, is precisely as you say. So you play with the initial condition to, let's say, pick up rare eigenstates of your spectrum, and this is what is happening here. Now, here is happening for a special integrable system, so that is not surprising everybody. In the other case, is much more surprising because you do not have integrability. You have a very simple initial state, and still you see these features. But yes, indeed, sometimes maybe this gets more clear. This let me. Yes. Thanks. Sorry, Olivier, I didn't